Hello everyone and welcome to Handmade Hero, show where we code a complete game live on stream. I realized something this week while I was just kind of, I don't even know what I was doing, probably just sitting around, and I was randomly thinking about the Raytracer. And I realized that the new system that we were making that does the grid style ray tracing is actually like way better than I thought it was, because previously, I don't know if this makes sense, but like previously I was just like, well, I don't know if this is going to be faster. You know what I mean? I was like, what, it might be, it might not be, but it's kind of hard to say whether it will be faster or not. And I realized that actually it's not only going to be faster, but it's going to be way faster. And let me show you why. So I'm pretty happy. I'm like basically positive that the latest Raytracer is the one. This is the one I'm going to use. So here's grid ray tracing for light probes. So I've literally never seen this mentioned before, and I'm guessing that's because either I forgot and it was mentioned before, or I just haven't read enough of the papers on this or something. But this is actually so obvious when you think about it. It's like, how could you not do this once you build a system like this? So in a grid-based ray tracer, if you remember what I said was I was like, well, all right, so the way this would work is we bin everything into the grid. So, if there's a thing that you could hit and it's over here, or things that you hit, we just put them in the various grid spaces, where those things exist. And then our ray tracer just does basically like what amounts to sort of a Bresenham-like walk through this thing. And we can compute those walks because since our ray paths, our randomized ray paths are pre-computed as well, we can just pre-compute those walks too. And so what I was thinking is like, well, the question that I have in my head is how, we know that this, thing might be like 32 by 32 by 32, right? And so in a typical case, I don't know how many grid squares you would expect to encounter, but this number could be like relatively high, right? Like, and if you were on one side of the grid and you were casting towards the other side of the grid, then, it could be as bad as like a full diagonal walk. And that's not the common case. The common case is probably more like 50 grid cells or something like that. But that's still 50 loops through the iteration of loading leaves, and it's just a lot, right? And so I was like, well, I don't know, like that could end up tanking it. It could be that in general it's just not faster. So even though the loop itself is probably a lot better than the AABB tree descent loop, But then I realized something. I realized that early termination is totally awesome, right? So here's the thing. Suppose you want to put a hard bound on how long this thing can take, right? And you just want to say, I don't want that case to ever occur. Well, we have light probes at every grid square, right? So if we just instead say, look, this thing operates in like a 4x4x4 or like an 8x8x8. That's it, right? We don't care how big the total voxel is. We only care about a subspace of it. Then what we can do is do the raycast in like a local region, like let's say like this. And when this thing goes like more than 4 squares, we just stop. And we look at the light probe in the square where we stopped, and we use the light coming back in this direction as the answer, right? So basically what we can do is we can trade light propagation speed for computation time and make it so that it takes maybe 2 or 3 frames for light to propagate from all the way on one side of the map to all the way on the other side of the map. But we can put a hard bound on the amount of time that raycasting takes. And this is not something we could have done with the AAB at all, right? So previously we had considered this, and there's a lot of schemes that do this sort of thing, right? That are similar to this. Like there's a lot of schemes that you see, like with AABBs, we even tried it a little bit by basically saying, look, when a ray gets to a certain distance, just use a higher up thing in the hierarchy, in the ray hierarchy, and return whatever light that thing was going to be. You know what I mean? But that's a very bad approximation. This is a very good approximation. We're actually taking whatever the local light transmittance was in that area and pushing it back, right? So actually, it's quite a bit more accurate than the way the AABB scheme was working, because at least we determined that you could get there, right? And that you were in the locus of something that was producing light in that direction. So I feel like this is actually really good, and it doesn't cost you anything. We don't have to build a secondary scheme like you normally would. Like with the AABBs, we had to build a secondary scheme. We had to actually track lights up the AAB. We don't have to do that on this. So I think it's really pretty awesome, and I'm not sure why I haven't seen it mentioned before. It's basically like free irradiance caching that you just get, because if you were building light probes anyway, why don't you just use them? I'm sure that's somewhere, and if someone wants to go find the paper, that would probably be nice to be able to post. I'm sure there's like a Eurographics paper from 2007 or something called like Light Probes for Grid Ray Tracing or something. And I never probably saw it, but it's just worth noting. So this is like basically you get irradiance caching for free if you were already doing an irradiance cache for your render time. If you use the same data structure as your light probe spatial index for your collision detection, you get this for free. And that's the thing that I hadn't seen mentioned before. It seems obvious, so I'm sure it is out there. It's just I hadn't thought about it, and now I have. So that's definitely what we're going to do, because that means we could go as low as 1 grid square if we wanted to, right? And just have slow light propagation, but instantaneous ray tracing, basically, to like reduce that time down. So I really think like it's really pretty good. So the only thing that I think is the only thing that it doesn't do perfect is that previously the loop had only one termination condition, and in this case we now have 2 termination conditions. And you know, that's not fabulous, because before the termination condition was you got to the end of the grid. Whereas now the termination condition has to be you got to the end of the grid or you took too long, right? And what we can do there is just like count how many leaf iterations we've done, you know, or something like that, and just use that as a termination criteria to enforce a sort of known upper bound on the compute time. And so adding a secondary condition there isn't the best thing in the world, to be sure, but it is at least something that we, you know, the amount of savings that it would produce is pretty vast. So it's not like we're adding a check to the loop for no real reason. So I would say that's pretty awesome. Like, I'm pretty excited about that, because that pretty much gets me out of the weeds on performance by taking out by putting in like a dial. We can just adjust so that on faster computers we just have faster light propagation, and on slower computers we just have slower light propagation, rather than having to like really stress over the optimization of this routine, and like if we can't get it fast enough then we're really dead in the water. Now it's kind of the opposite. It's like, look, we want to optimize this routine because it will ensure that we get higher quality lighting, but we don't have to worry about the optimization from a performance standpoint, because we can really turn down the distance and then produce a faster routine just by having it take longer to propagate the light. So I think that's awesome. All right. So that's where we're at. And I guess, like I was saying, so if you look in here, so here's the new routine, and you can see how it works. We load up a spatial grid node here, and then we, because we've got the start index and all that stuff, right? So we load up a spatial grid node, and if it looks like it was a terminator, so if it was on the apron, then we stop. Otherwise, we keep going. And like I kind of said before, there's sort of this issue of the ideal thing now, if I could, would be to just have a single count that said, how far have I gone? And that way I can just stop at that point or something. Because that would handle both cases. It would handle not walking outside of the grid, and it would also handle it would handle the termination for speed. But the problem is I can't really produce that value very conveniently. So if I did want to switch this over to a for loop that was just here and it looped over some number of things, the reason that I can't just do that trivially is the calling code doesn't know how to produce a number from a particular grid walk that it's got, a table-driven grid walk. It doesn't know how to produce the correct stopping value from that thing. And I can't honestly in my head think of how we would do that conveniently, because since the thing, has like an uneven pattern, it's like, oh, well, it will go like 2 in X, then 1 in Y, then 2 in X, then 1 in Z, 1 in Y, then 2 in X, then 1 in Y. Like it has this sort of pattern as it moves through the grid based on the direction of the ray that's being cast. The problem that I see there is I don't know how, without actually doing the walk, I don't know how to accurately predict which grid square would be the last grid square for that to go to before it leaves the actual bounds of the grid. And all the things I can think of that would produce an accurate answer for that question so that we could just have one count, none of them seem super compact or feasible. Like I can't, in my head, think of any way to really produce that number quickly. And so I feel like the apron solution is just an easier solution to the problem. So what that means for me is like I kind of just want a cost here, right? So we want a cost metric, and the cost metric is maybe initialized to some specific value. Maybe that specific value is something like 16. I don't know. But we'd basically say, while the cost metric is greater than 0, right? So, or, I could just say, while the cost metric is not 0, right? As we come through this code, we could look and say, well, every time through this loop, let's say, we subtract 1 from cost metric. So every time that we've tested against something, we go down. So this way we can set the number of leaves to something, and we can just say like whatever that number is, that's the most we're going to do. So we test 8 leaves total or something, right? And then we know that either we got to the edge of the grid so there's nothing left to look at, which terminates in this case, or we got to a point where we tested so many leaves that we just don't feel like it's profitable to keep going. It will be too expensive. So let's just use whatever actual location we have as our lookup, right? And so if the cost metric here, if we exited on getting to the apron, we know the cost metric is still greater than 0. Whereas, if the cost metric equals 0, then we know that we haven't done that. The problem is that we've looked up the grid index here, and we don't actually know at that point whether this grid index is valid or not. You know what I'm saying? So our cost metric may have been reduced to 0, and we may still be going, right? So it may be that this is not great. Like it could be that really we probably want to do that, and we just say, all right, so if we exited here, we know that we don't need to do a lookup, but maybe here we would just say if cost metric, has decremented to 0, then we, do a compute voxel irradiance at kind of a thing. And we need here to just say, get us the voxel irradiance coming back in this direction. You know what I mean? So I think this is all we really need. And once we've done that, I think we also probably don't need to do this. So this routine gets a little more complicated because I think... Well, yeah, so I think what happens here is kind of confusing. I hadn't really thought about this yet. But this routine is actually not as good as it should be even already, because I realized this loop should stop if you hit anything. Because you know that all of the things that are further on in the grid are later collisions. The T is strictly increasing the entire time. So actually, this part should probably feature a way to break out of the grid as well. Meaning, there are 2 termination conditions here, and only one of them does this, right? So I think it's actually... it looks more like this, which is to say that when you do a test of the T values, so when we have this here, we would just need to know, like, are any of these valid in the first place, right? And if they are, then we can stop. So we probably want to do a mask move at that point, just for our own... like testing purposes, like hit, something hit. And in here we would just do, if something hit, then we do our post-amble, so we finish figuring out what the ray is and we break. And so I feel like it actually kind of looks more like this, where inside here we do have an unpredictable branch that's just the termination branch, because it's probably way more expensive to keep marching rather than stopping when we first hit something. So I think maybe that's a little bit closer to what we need. And the something hit here is really just a mask move out. It's, one of these where we just take... And the mask that we got here, this is just telling us if we got a hit at all. And when we extract that mask, we can just OR it into the mask we've got. And then on termination, if any ray ever hit, then that's our termination. So the only thing that this doesn't do correctly is there is like one side case there, and I don't really know... how we would want to fix this, or if we would want to fix this, but... Oh, wait, no, we don't have to fix it. Never mind, I take it back. So the thing that I was going to say is, if you imagined inserting these boxes without clipping them, meaning you didn't shrink them to the size of the grid square, then you would have to worry about potentially registering a hit of a I got to draw this. I can't. You're never going to understand what I'm saying without a diagram. Sorry. Let me just draw it for you. Let's suppose we have our grid, and we have a box that spans multiple grid squares. Then we have a raycast that originates from one of our cells for the light probe, and the pattern that it goes is maybe actually fairly like oblique to the ray, to this, right? And let me see if I can draw a really good example here. So, let's suppose it's going like this. through the system. And let's suppose there's a tiny box here, right? And a very large box here. If we didn't clip the AABs that we insert to the grid squares, then when you enter this grid square, this box, which is large, is obviously registered as being part of this cell. When we do our collision detection, we will find that we hit it, and it's over here. If we then stop, because we early terminate and say, well, we know that anything we hit in this grid cell is closer than this grid cell by definition because we entered it first, then we will never find this collision because we never looked in this grid square, but it was in fact closer. So all I wanted to say was, as long as we clip, which we will, because there's no reason not to, it's AABBs. Clipping is just calling min and max real quick before you push the thing in. As long as we clip, we will still be accurate because this box will not register a hit with the ray. So we'd be fine. That's all. Make sense? Hopefully. So I will add, so that we don't forget, I think that's a good thing to do anyway, but just so we don't forget, when we do build the spatial partition for the lighting, I just want to make sure that we remember that. So I'm going to put a big old to-do in here. So hopefully that makes some sense. Why am I talking so quiet? I've been having a lot of allergies lately, just for like several months, really, and it just like it aggravates my throat. So I've been trying like talking more quietly, just to like it. I don't think it really helps though. It's just it. I don't know. Allergies are bad. I wish I didn't have them. All right, let's do this. So anyway, when we're doing our move mask, yeah, so we just want to make sure that we get back whether or not any of these things hit. And so this T-valid and less than T-ray is all we really need for that. We basically already got it. T-valid would also do it. Either one really would be fine. But anyway, so what's the problem? Move mask, right? It's just move mask P. So that's totally fine. So now what we have mostly is this issue here, and I believe we kind of have to partition this routine a little bit differently. There's no reason for a sample P here. I mean, we could do it, and maybe we will for now, but like in the future, that's not really necessary at all, right? Because we already know which grid square we're in. This grid index value here is all we really need. And so we don't need to do any of this part of that. We do need to do the sample normal part, but of course we already know that because it's just the negative of the ray direction. You know what I mean? So that part's pretty straightforward as well. So I think what we want here is to partition this out. And so instead of compute voxel radiance at being something that by default takes a P, we'll probably do like compute voxel radiance at in a way that can also take a grid index. So if we were going to do it that way, what we would want is this same code, like so. What does outgoing mean here? Outgoing. So I'm not sure what the outgoing part of that is. It looks like that's some kind of what are we passing to this? So we're passing emission direction. So I feel like since we haven't done the lighting quality pass there, I guess like, yeah. I guess I'm not sure what to make of this. So the way that we're doing this currently is we're just looking at how much light was coming from the normal direction, which I don't think is right. I mean, there might be a reason why you would do that, but I mean, I don't think so. Like, you would really want to be using this value, right? Or more specifically, the negative of that value, because if you assume that this thing is lit by the light probe's irradiance, which is the approximation that you use when you have light probes, you assume something in the cell of a light probe is getting lit by the light that light probe has captured. That's the point of the light probe. We would want to sample the light coming from the direction that you would bounce off of. Because this is, even though this is a diffuse surface, it's still, going to be reflecting the light via the reflectance function. So I'm not sure that sampling the normal is necessarily the most logical thing to do in that circumstance. So that seems a little bit busted. I'm also not entirely certain why you would ever need to pass the normal at all, because you know what you bounced off of. And so you don't really need that at all. So this kind of feels a little bit dumb and probably not really what you want. I'm going to leave that for now. I'm going to put a to-do in here that just says this should probably actually use outgoing instead, but we need to do a lighting quality pass after the optimization phase in order to really nail this stuff down. So I think what I'd like to do here is let's just ignore that for a moment and say I'm going to put the part of this that actually does the sampling into a separate routine you can call with different parameters. So effectively here what we could say is the voxel index parameters that we produce and the UVW values that we produce, these are, and in fact I could actually just make it be I could make it actually be that blend as well. Let me think about this. So the thing that I'm not sure about is like, how do we want to actually terminate the ray? And if we do that, what's the T value that we've gotten so far? Because we could also blend these together. So you know what? I guess, you know what? I'm going to take that back. I'm going to say maybe we can just use this. And we just need to be a little bit more careful about this. So let's just say that maybe what we do is we actually call the complete version that actually does the blend. And what we do here is we compute what we think the sample point should be based on how far we would have come so far. You know what I mean? So what we could do is we could take the ray origin and the ray direction. We could just move forward by a t-value which could be baked into the tables. So we would say early termination sample p, start where the ray origin is, and go however far we need to go. And so there's like a t terminate here. And the t terminate is just like we've gone, you know, this far in the ray. And then we would sample the voxel at that point. So that would take the solution, the diffuse atlas, the sample p, sample n, yeah, going. So in here, right, the early termination sample p is the location, and then the two normal values in this case would be the ray direction, right, in both cases. So that's like where we want to sample the light coming from. And again, we have to change that compute voxel irradiance at to actually be like more logical about how the light's getting sampled. So we'll see. Now, since we know that on exit here, we are producing what is effectively a compute voxel irradiance sample anyway, because we know here that we were going to do that. It's also entirely plausible to me that we could try to make these both kind of happen together so that we don't have two calls to that function. It's a little bit obtuse as to how I would do that, because if you look at how this works, you know, we kind of have some stuff that's done wide and stuff that's not done wide. And so I think for the final version of this routine, when we try to streamline it one more pass at the end, I think what we might want to do is try to collapse these two. So, you know, I'd put a to-do in here that's like, oops, to-do. This keyboard is hopelessly off-center today. My desk is a mess. This is only for streaming, this desk, and it gets kind of gunked up. So I want to collapse compute voxel irradiance at calls into one. So for now, I'm fine with calling it twice, but I think that's something that could be collapsed. And what we could effectively do here is have this code all just be shared. So in other words, this stuff would all just happen exactly the same way as it was happening before. And because we know basically all of the ways that we break out of the loop are going to do this, the only one that isn't is this one. But this one actually still sort of is, because we could at that point use effectively like a skybox or whatever as the thing we were sampling. So you could imagine, like, just to give maybe a little bit better of a, just to sort of illuminate this a little bit, and maybe I can even just do it right now. If we were to do something more like this, where we have these situations where we break out of the loop, in fact, this doesn't need to happen anymore, too, it looks like, because we now have tested just using the... Yeah, so we now know, because of the mask move here, we actually now know that we hit. So we don't need to do this part either. Let me look at what T-ray single is actually doing. Is it doing anything? Yeah, it doesn't. So we can actually eliminate this branch entirely because we've already done it, which is nice. It means that at least we're not introducing another one in there. So here you can say, all right, we do the something hit. If we did, we can early terminate. If the cost metric was a problem, we'll terminate for that as well. And then we'll fall out here, and we'll fall out into a way that's going to use a couple things that we have that we need to propagate outwards. So if we look at what those are, there's like probe sample P single, probe sample N single, like emission direction. And we want to grab those, we want to basically produce those in each of our cases. So in the case of probe sample N single, right, this is what we've got at the moment. Like so. Probe sample P single, same thing. And so now these two could be pulled out of this loop as exit parameters, right? So when this gets pulled out, and similarly, like we could say for the transfer PPS here, like I said, I think we want this welded in. So we want that transfer PPS to actually get sampled always, and we'll make the adjustments that make that happen properly in a second here. So we know that we need to produce these two, and we will just assign to them now in these two cases and then let them fall out of the routine properly. So that's good. And then, so in this case here, rather than creating a new value, we would just say probe sample p single equals that termination place. We haven't quite figured out how we're going to get that value yet, but it's probably just going to come from the table. And then in terms of the probe sampling and the emission direction, which is the other one we need here, that's going to be negative rad single as well. We're always sampling that back bounce, so that's, you know, in either of these two cases, right, we're going to be doing something like this. I think it's just whether it's the positive or the negative, because either we didn't actually hit something to bounce, in which case we need to take the positive ray direction, or we did hit something to bounce, in case we need the negative ray direction. Or I think I said those backwards, but you get the idea. So we'll make sure we set those properly as well, but I think that's mostly what we need there. That's rad single. I think these are actually both, because we want to know, well, no, I guess that's not true. So these are both pointing in the same direction. But I think this goes away because I don't think we want to be passing the normal to that routine anymore. When we do a sample, we just want a sample, right? So I think compute voxel radiansat just wants to give it the direction to sample. And then, you know, you assume that the person who calls compute voxel radiance like already did that, already did that work for you. Okay. So I think our for I loop is good now. That all looks right. So we do the leaf test. We go there. We for yeah. So I think that all looks good to me. I think that's all good. So if we take a look at what's going on here. Problem that we're getting here is that we don't have the shuffle value that we actually need to extract our other values, like our hit ref color, these sorts of things. And all of these computations, as you can kind of see, they're operating on the 4-wide version. So when we initialize that, you can just kind of see what we need here. So when we produce this hit ref color here, this actually probably wants to be pure white because we wouldn't reduce the transmittance in the other case. So this is actually going to be like V3 4X 1111, right? We're just going to assume that we don't reduce the emission in that case. So at that point, all we need to do is make sure that the shuffler itself is its own thing that gets persisted. And we need it to default to loading something that will not, something that won't just be bogus. For this case, since everything will be the same in the case where we exit early, we can just assume that any of these are okay. So the 0 on the shuffle table is fine. I guess I need to do that though. So really anything here, it doesn't matter which one we pick, will be fine because any of the lanes are okay at that point. You don't need to take a specific one of them. So we'll just pick 0. I think at that point, the only thing we don't know is the terminate, and I think that pretty much has to come from the lookup value here. I could be wrong about that. Yeah, I could be wrong about that. I don't know. So this load where we update grid index, right? Which actually can happen at the very end of the loop. It doesn't have to happen anywhere in particular. This is a little bit off. That's supposed to be in here. That's supposed to be there. Then we do that, right? Yeah. So this doesn't really need to be an else. I mean, that's a break statement, so we could simplify the indentation here a little bit too by just doing that. Because we know that, like, well, if you break, you're not going to go any further. So I think that's what this should look like. And I guess the thing that I was talking about before is the walk table could give us that t value that we needed. So the walk table could pack those two things together. So for example, the walk table could be something more like, all right, there's a grid index. So we basically say, like, what's the delta on the grid index? So this is like the D grid. And then we can also say that the t terminate value is the t terminate, right? So I could pull those two things out, and that's relatively straightforward. I'm just not sure that's the best answer because it does make those tables a lot bigger. It makes them a lot bigger because they have to now pack a 32-bit value in addition to what was just previously a U16 value. And that's probably not great. I mean, So if we were to do that, it's a little bit, it's not fabulous. You know what I mean? It requires us doing this. You know? So I'm not sure that that's great. It means that the walk table entries are actually quite a bit larger. They're 3 times larger than they were before, which means that the caching on them is 3 times worse. And I don't know that that's particularly fabulous. Now, it might not matter, but it's definitely worse. It's for a huge benefit, meaning we really want this. So if that's the most efficient way to do it, it still is a massive win probably. But the reason that I bring it up is just because there may be a smarter way to do this, meaning there may be some way that instead of doing that, we could do something else where we just automatically propagate the t value somehow. Like by the way we step or something, we can just keep track of it for free or something like this. So I don't know, but I just want to make sure that we're aware that that's, possibly not the fabulousest of things. Okay, so let's take a look at the walk table now. Here's how we're getting the walk table. So what I really want here is for the light sampling walk table to just instead be walk table entries, and we know that that's, pretty straightforward. There's not really anything fancy we would have to do there. So where we go to light sampling walk table, I assume that's probably in the INL file, and it is. So that's going to be a walk table entry. And so that's probably not going to go in here. That's going to be something that's generated by our subsystem. So it's going to look more like that, right? Okay. So I think that's everything. And so the question here is just, is there anything else we really want to do before we go through the work of actually producing the tables for this system, which is going to be pretty much the majority of the work we're going to have to do? And it doesn't, I mean, it looks to me like everything's fine. What I really need to do is just validate the performance of the routine and then start pulling out all this crap, because there's so much cruft in here now that doesn't really need to be there. If this does turn out to be as good as I think it will be, then we can just vaporize like half the code in this file, because it's all for stuff that we don't do anymore. So looking at the cost metrics here, that stuff looks right. I think that's a pretty sane way to do it. So we can just adjust this cost metric as necessary. And, you know, you could make it 255 if you just wanted to basically raycast everything always. And you could make it as low as, you know, 1 or 2 if you wanted the worst possible thing. The only thing it doesn't account for right now is loading out the spatial grid nodes themselves, which is some cost. So we may want the cost metric to also take that into account, but I mean, who knows, right? So I'm not sure if we want that. Like, what we could do is have there be a cost metric. I mean, we could make this a little bit more expressive, right? You could say something like this, where you said, okay, there's a cost metric, maybe it's 16 or something like that. And what we do here is every time we process a leaf, we consider that to be a cost metric, a significant cost metric. And then we also have, you know, just a constant decrement. So maybe the cost metric here basically says, hey, like, you know, there's some decrement through here that we do every time. And this will be free because, you know, there's so much wide, like this is all SSE, there's almost no scalar. So, you know, this can just happen. I mean, it could happen like, you know, right here and be basically free. It will just snuggle in with the SSE ops and be free. So we can just do that. And then down here, we just have a constant cost. So every time through the loop, it also goes down. So this way we can basically say, you know, every one of these is a cost. And we could make this more expensive too. We could say like to do, you know, what is the actual cost here relative to the base loop. So, you know, I don't know what this value should be. Maybe it's 4 times as expensive to do it. Maybe it's twice as expensive. Maybe it's no more expensive. I don't know. But, you know, something like that we would use to adjust the cost that we're paying. And so we know we could do like 16 grid squares that have nothing in them, or 8 grid squares that have 1 set of colliders, 4 grid squares that have 2 sets, that sort of thing. So I think that's fine. So I think we're okay. So we process all of the leaves. We look to see if we hit anything in there. And we have to process all the leaves. We can't just stop as soon as we find a hit, because inside one cell we're not sorted in any way. So we need to check them all to find the closest one. I think that all works well. We output a probe single and an emission direction in both cases. So like, right, you can see those all happening here pretty cleanly. Shuffler gets loaded in here. It doesn't get loaded in the other case because we don't care. It can just be the default value. And then we fall through. Now again, we probably don't want this exactly. So what we want to do here is probably having, we want a location to probe that would give us, in the case where we don't hit anything, we would want there to be like, I mean, I guess I don't know what we want to do with like moonlight and stuff. It may be that we just want to put moonlight tiles. I mean, I think that may be just a better idea, because I feel like moonlight tiles are better than what the previous solution we had was. And so I think what we would want to do is actually hit those things and produce the correct irradiance for those things. Like the emission for what we hit would be something that could be presented, you know? And we could have ways of having directional emission that come from, you know, things we hit. Like when we load this stuff up, we could have ways of doing directional emission that way. And I'm just not sure exactly how we want to fold that into the routine. So I think what I'm going to do is say that I don't really care about that at the moment. So transfer PPS here is always going to get set, and we're going to work on how we actually do ambient lighting, or I should say sky lighting. We'll look at that a little bit separately because I don't think we have a really solid idea for that at the moment. And I'd like to do something different than what we're doing now, because we already needed to figure out a solution for how we were going to prevent moonlight from affecting areas that don't have ceilings, but that are supposed to be underground. Do we just put a ceiling all over them? You know, what happens there? And I think I don't like that solution because it just means we're adding a bunch of extra geometry we have to deal with for no reason. I think what I would rather do is for the above ground regions is add the geometry there, because we're actually adding geometry that says, hey, there's light here that you need to pay attention to. And that geometry seems more sensible because it's non-occluding geometry. And so it doesn't have to have a special renderer thing to know how to deal with it. If we put ceilings over everything, we kind of have this nasty problem of having to be able to see through those ceilings. And so they have to be placed properly, and, you know, you get the idea. So we'll deal with that a little bit later, and for now I think this is correct. So I think what we mostly have to focus on now is generating the tables and the spatial partition. Let's go ahead and try to do the spatial partition first, and then we'll try to do the walk table second. I don't know what the status is of this exactly at the moment. I assume this should just crash, right? Because we haven't produced any of this stuff, and so it should be looking up into no man's land in both cases, right? So if I run this, I should get a, well, let me run it under remedy. So if I run the lighting profiler right now, it should just die. Yeah. I guess I'm not sure why it died there. Let me recompile in debug mode because it doesn't seem quite right. May just be a misreporting though. So I'm not sure here what's going on with that. It looks like this is because that's okay, so that's plausible, I guess, because it looks like I changed that up, right? So the HH light I meant inl. Yeah, so you can see the sampling. These here have not actually been initialized. Although, why did that when did I actually change that over? I don't really remember doing that, to be completely honest with you. So sample directions here in this case is what? Who passed that in? Like who actually passed that? Fullcast passed that? Okay, so yeah, you can see what happened here. It was this stuff, right? So yeah, that's totally fine. All right, so I have to go ahead now and actually build all these tables like I was saying, and let's actually start. So the first thing that we're going to need to do is an end lighting computation. So in end lighting computation, I'm going to need to actually implement the spatial partition build, although it looks like we put that in begin. Did we? Wait, build spatial. No, we didn't. Okay, good. I was like, that doesn't belong So here's the grid build, and you can see that we sort of did a little bit of it. So let's go ahead and uncomment it and actually try to make a real version of it. So the first thing you can see here is it goes through and it just tries to figure out like where these boxes exist in the voxel. And we have a get voxel index for P sort of thing, don't we? I thought we had something like this, but I guess it's rolled into compute voxel irradiance. But I mean, this is it, right? So this is the thing that does that computation. So if we wanted to have a V3U that was get, I guess it's technically a V3S in this case, because it could actually be out of bounds. I don't know to what extent we exactly want to handle that, but because these should never really be out of bounds in that case, but we can talk about that later. So in this case, if I have a V3S and I say get voxel index for P, I want to do exactly this. And I assume that it would be safe probably to make this be a thing that happens here as well. But I'm not going to do that because since this has kind of a slightly different thing, it needs the UVWs as well. I'm just not going to put that part in there. So I'm going to have get voxel index for P here. Take the V3, whatever the P is, and the lighting solution and produce that value. So it's going to do exactly the same thing. It's then going to produce the voxel index value that we expect, and it's going to come back here. So when we call this and we get it back, this is all totally fine and dandy what it's doing here. And then we need to do some actual work to chain these things together. And what this is doing is this is trying to basically figure out how many leaves go in each node, right? So what I need is a temporary storage solution. I need something that will temporarily store the data that we're actually talking about. So I basically need scratch space for that. And I know how much scratch space I need to do the chaining because I know that it's the number of boxes that we actually have. So if we take a look at the lighting box structure itself in here, what I can do is I can start to play around with this stuff because we know that, like, for example, we don't use these things anymore. They're just not part of our system anymore. So instead of using like these child indices, that sort of stuff, we can just use this for our chaining. So what I'll do is I'll just say, okay, for every one of our grid nodes, temporarily what I'll do is inside the whatever the actual structure here is in lighting. So for this, right, what I'll do temporarily is I'll make the start index here. I'll make that be the thing that tells us what the first element in the grid is. And then what I'll do is chain using that temporary value in the lighting box. And again, a lot of this stuff is way, like, really kind of ugly right now. And the reason for that is we're trying to overlay multiple systems on top of each other at the same time to test to see which one we're going to go with. As soon as we actually definitively make the call, like, okay, it's grids, then what we're going to do is we're probably going to rip out all of that stuff, right? And then just do a pass to clean up everything to make it look nice and simple and remove any of the other things that we don't need. Because there's so many things we don't need. Like, even these split box things, like all that just goes away. Because once we're gridded, we don't use that anymore. So effectively, like, getting rid of all of these spatial hierarchy stuff, all of that stuff, that's a pass we have to do, but I just don't want to do it yet because we kind of want to finish this part of the testing first before officially ripping all that stuff out. Okay. So if we push forward a little bit further here, what we know here is when we want to do this chaining operation, what we want to do is we do want to pull out the node. And that's going to be this. And in order to pull out that node, we need to have some way of getting a grid index from... so we've got spatial grid nodes. We want to do something that allows us to get a node from an XYZ value. So we want to do like something like solution spatial grid nodes. And we want to add like, spatial grid node index from here. And we know how to produce that because we know what these voxel dimensions are, so that should be fairly straightforward. But it does require you to know what those are. And there's a couple of things here that are a little bit squinky, specifically like, well, you know what? It doesn't matter. We'll talk about that when we actually build the walk tables. But point being, we know that we want something that does this. And in order to build that index there, we need something that's going to... actually, didn't we do this? Yeah, never mind. It's right here. This is what it is. It's just that. Right? And so as long as we know what the voxel index actually is, then we don't really have to worry because this will produce that value from the voxel dimension anytime we actually want that. So let's see here. If I go, didn't we have a thing that we sort of sketched out, the thing that built the walk list? Here's compute walk table, for example. Didn't that also do this? I guess it didn't really. I guess it did it sort of in line, well, which is cool. All right, so anyway, assuming that we get the grid index here, off we go. And there is sort of a little bit of a difficult thing here that we have to consider how we want to approach. And that is that we would like to have an apron for this scenario. We'd like to have the outside of the grid have stuff in it that tells us that we've gone too far. So grid index from is like really not, it's hard because we sort of have two types of grid index, which it's really bad and error prone to have that. I often find myself making mistakes where if I have two indexing schemes, I accidentally use the wrong one, because especially when you're writing efficiency oriented code, you tend to have to drop things down into like very specific even SIMD operations. And you can't afford to use types and type checking to help you there a lot of times because compilers are just really bad at this sort of thing. It's unfortunate. And so the problem that you end up having is that, like in this scenario, I need two types of grid index. I need one that has an apron and one that doesn't. And we have to be careful to use the correct one in the correct circumstance. What would be best is if we could just have only one way of indexing, but I don't know that that's really theoretically possible in the case that we have here, because we need to have our lighting atlases be as compact as possible. We certainly don't want to bloat them with extra data that we don't need, and so it's kind of unfortunate. So if I could have gotten away without an apron in the grid raycast, I absolutely would. I just can't figure out a way to do that. The most optimal way would be to get rid of that and have some other way of doing it, like I said, but I just don't know how to produce a walk value that's always guaranteed to hit the end without doing a fair amount of computation beforehand, or just really bloating the table size by having like a secondary set of tables that you look up into to figure out how far you could go based on a particular array and a particular location. It's just not great. Okay. So I'm going to have two of these for now, and maybe with an eye towards if we can ever remove them, that would be great. But, if we can't, we can't. So in this case, well, I guess I could say, we just have to pass the correct voxel dim is the other way to look at it. So in the voxel dimension here, we should have stored in here some kind of a V3. I guess we even kind of know when we come in here, where's the voxel dim values? They should be in here somewhere. Like just the voxel count, right? But oddly enough, I don't see that in here anywhere. So I don't really know where that is at the moment, but effectively what we need to do here is when we have this grid index from, right, we want to pass the voxel dim in here. And so I need something that's like voxel dim with apron. And we need that to be something that we use to get these grid indices. So we need it to look like that, and I guess we'll figure out where we want these stored and how a little bit later. Maybe we'll actually, what we could do is just put it in here and say, hey, you know what? Why don't you tell us what that is? And we don't really care where you get it, just get it. So then we'll go through here and we will produce the voxels here. The get voxel index for P should be fine either way because we don't really care what the offset is of these. So in this case, when we do the grid index from, we could just increment this value by something to account for the apron, right? In other words, if we want, we can just do this. So this computation is can always be done the same way. We don't have to worry. This computation can always be done the same way. We don't have to worry about the apron when we're doing that because the voxel always occupies exactly the same volume. There's just a question of whether there's like an outside ring of invalid voxels that are there to stop the Raycaster from going too far. That's really all we're talking about here. You know what I'm saying? So yeah, that's all. That's all there is. So in this case, if we go ahead and load up one of these nodes, then what we want to do is chain whatever box we're talking about onto that node so that we know that that box has to be processed in that node. Oh, you know what? This is not as easy as I was making it out to be. So since boxes can occur, we may need scratch space for the boxes as well. I thought we were going to be able to get away without it, but since boxes can occur in multiple nodes, I guess there's really no way quite to do that. Yeah. That doesn't seem plausible because as we go through here, right, we're going to put this box on multiple, potentially multiple grid squares. And that just, I can't think of really any way to do that properly. There doesn't seem to really be a way. So we will need scratch space for this as well. Like we'll need some way of building a chain here that gets larger. I'm not thinking of anything bright for that. So I think we may just have to use temporary memory here. I don't see what else we're going to do. So when we come through that to the end lighting, I feel like we probably need to get temporary stack memory here. And in order to do that, I just probably want to take a look at where is the frame data? Because we previously had a thing where we would just have extra data for a particular frame, right? And it's a little scattershot in Handmade Hero because, you know, we don't really get much time to actually clean things up. So there's a lot of times when things are a little bit more scattered than they would be, especially because I can only, you know, I have such a limited amount of time I can really spend on it on stream. It doesn't really get the kind of polish that, you know, I would normally get to do. So I'm not really sure we ever quite got the per frame arena. Like it's not really used in the way that you would normally use it. it doesn't really get much use because we added it, but we never really did much with it. And you can see here that, there it is. And a lot of people who probably should be using the frame arena, aren't using the frame arena because it got added pretty late, and then we didn't do a sweep through to, consolidate. A lot of problems could be solved with that. But what I'll do here is I'll just, we'll start using it in here because I know that we do want it here. So what we'll do is we'll just say, all right, here's our per frame arena that we're going to use. And we know that this is a temporary thing. We don't need it after we do our scratch operations. We don't need to do it. None of the things that we do here will persist. So what we can do is we can use the frame arena. We can generate as much garbage as we want, right? And I mean, effectively what these are is free garbage collection, right? We can do whatever we want. Doesn't matter how complicated. And then when we get to the end, it just all gets cleaned up for us. So at that point, we can just afford to say, look, when we're building these lighting superstructures, I don't really care how expensive it becomes to do, because you'll be able to use this arena to allocate as much temporary space as you want effectively, and it will all just get vaporized immediately after the lighting values are computed and output, right? So I'm going to go ahead and do it that way, and that way we can do it without worrying too much about, how do we fit it into the scratch space and having to do multiple loops over things or things like this. So let's do it. What I'm going to do here is say we're going to introduce, I guess, a secondary structure for this that's only used during build. I'm not sure that's completely necessary, but I'm not sure I see how else to do it. Where we just have lighting, temporary box. And all this is a really crappy simple buffer. That's all it is. It doesn't do anything else. And all this is saying, here's a way to do a direct iteration over all of the boxes that exist in the grid so that we know where they go. Well, wait. But we could also just do this twice. Yeah, you know what? We could also just do it twice and not bother. Let's try that and see how expensive it is. So suppose you just did this, right? And instead of ever doing any chaining at all, you just said, hey, let's just record how many things we actually needed to put in here in the first place. So for each one of these, we just counted. So we let start index, right, be the count. So, we clear it first. We do something like this. And we say, okay, clear all these, take the start index and use it as a temporary counter. When we're done counting, assign all of these in series. So we just go to each of these and say, we've got a total leaf count here. We go through and we say, for any particular node, the start index is the total leaf count, and the one past last leaf index is the total leaf count plus the start index. Obviously, we have to do those in the opposite order. I suppose I could do it the other way around, meaning this might be a little bit cleaner, because then it reads a little bit more straightforward. Does it not? You know, seems more right. You could even do this. So we effectively go through, we count once, and that's so that we can lay everything out in a tightly packed array. And when we're done doing all of that, we can then just do the exact same loop again. So we just do this a second time. We don't need to do any of this, right? Any of this chain nonsense here. And so instead what we then do is we just say, okay, like all of this stuff that we were going to do to insert things, we just insert them, right? And off we go. So I think that's okay. We just need to get the allocation stuff to work properly. And it's, you know, it's a little bit squirrely, but, you know, we'll work it out. So yeah, as these things get inserted, we need to figure out like how properly to insert them. And it is a little bit ugly because we need to kind of write them out in a packed format. And that may be kind of slightly tricky. But yeah, we'll see what happens there. I'm not sure, again, I don't know to what extent zeros will be acceptable as things that can't be hit. I don't know if 0, 0, 0 as the box min and box max will produce an unhittable box or a hittable box that if you hit it directly at 0, 0, 0, so you pass perfectly through the origin, if that will actually get hit. I think I would prefer to not have to do this initialization. I would rather be able to do a clear to 0. So I think I might change that to just more of a to-do. Oops. So I may say let's change that to more of a to-do at the moment, but we'll kind of come back to that later. Okay, so in here where we do, we loop through our box indices, we figure out where these things are going to go. We take our total leaf count, we count it up, we take our box indices, again, we go through them a second time, and now we try to actually pack them into where they go. Again, one problem that we're going to have here is actually looking at this. These need to be padded out to 4s. And so we want this to actually be like total leaf count plus 3 mod 3, right? Like, or and 3, I should say. So, sorry, and not 3. So we want to take and say, look, we want this to be padded to 4. And I don't know if we have an align for that. We do. So we could say, to make this a little easier to read, we could just say this, or better yet, could say this. And this should have been parenthesized and wasn't, which is kind of bad. I'm not sure why we did that, but that could have leaked operators all over the place, and we could have had bad results. So that should be fixed, and wasn't. Oh well. But point being, if we come through here and say, all right, so the total leaf count here will now be properly padded to 4s, then when we come through and we look at the indices, we now can use those properly. The other way we could do this is to use this divided by 4. You know, now I think about that, might be better. No, probably not. What we want to do is just divide by 4 at the end. That would be my assumption. I think that's probably right. Okay, so now we have the ability to push using, and we can use the frame arena for this. We now need a place to store all these leaves, right? Although I guess maybe we don't, like, again, this is why I say, like, these could all be allocated just on the frame. So I suppose yeah, like eventually we should just allocate these on the frame and, use the frame arena for it. Seems like the right thing to do rather than leaving them sitting around because they don't really need to sit around. But, so I don't know. I might say push array here and we just push on the total leaf count because we know this is how many leaves we need. So we just say, all right, push on the total leaf count. We know that we're using the temp arena in this case, and we know that what we need to push on are these spatial grid leaves, right? Yeah. Trying to think of like when I want to wrap this up. I might go a little longer today just to finish this up, but I want to take a quick break first. Yeah, I think I might take a quick break and then I might want to try and finish this routine even if we go a little bit long. So hold on 1 second. All right, I got some bunny fruit snacks here that should do the trick for energy. I think there's a bug in grid index from. There might be. Let's take a look. All right. That will surely be enough sugar. What's the bug in grid index from? It looks like it's missing a Z, actually. Yeah, that's weird. Not sure where we got that from. Because the equation should be, it should look like this, right? It should be like x is an offset that's just used by itself. Voxel dim x times the y coordinate is how, because it's y goes by x slices, is how far the y offset is, and then voxel dim x times voxel dim y should multiply z. And it looks like that's kind of busted, yeah. Because that, I don't know why, I don't know how that ended up being that way, but that, yeah, not good. So yeah, that's what we should have. For sure. Thanks for that. Because, yeah, voxel dim z is not necessary. That's just a bounds at that point. All right, so what do we want to do here moving forward? So this is actually just the p-value. Doesn't have to be sample p. So let's get back to what we were doing. So here, yeah, we want to allocate, when we run through the box indices, we want to allocate the total number that we counted that we needed, which we know will be this. So we do that. And then for each time we run through here, we want to do this again. I don't know what this is complaining about. Oh, I guess we don't have a v3u, but that's fine. We'll just use v3s. We don't really care. We don't need it to be an unsigned for this particular purpose. It's not necessary. Does not take get voxel index for p, takes the solution, which makes sense. There we go. Okay. So these have to be S32s just for compiler warning nonsense that shouldn't actually exist, but it's fine. And we will produce, I guess you know what we could do? So since we have knowledge of what the furthest out value would be, we could just produce that value. So for example, if we do this and we say, what's the max grid index? Well, we know that the max grid index in this case would have to be the total voxel dimension with apron, right? I think. Because that voxel dim with apron, if we ask it for this dimension and we pass the highest value, that should give us back the highest index, right? So I think that's sufficient. I don't think we need really anything else. So grid index from is voxel dim xyz. Yeah, so this is just x, y, z. And that's it. Okay. These both were passing that value. So you know what? Let's make this actually take a v3s, because why not? So this way we can just pass the triple as a triple and leave it at that. Okay. Problem solved. Okay, so now let's see here. We've got our total leaf count. Obviously this needs to kind of be a U16 in this case. And you know, I guess now that I'm thinking about it too, like if we wanted to, we could expand this to not be that. We could use larger storage, and maybe we should. Depends on whether we think we want more than 65,000 of these. We probably don't, but who knows? I mean, maybe we could just handle that. We'll see. I'm going to leave them as U16s for now, but in the future we could consider doing them differently. All right, so in this case, we need to make sure that we never overflow this value. And so in this particular case, we would need to say, let's make sure that this thing doesn't, you know, let's assert total leaf count here, or assert that, well, you know what? We'll sum it as a 32, and we'll just assert that we can safe truncate, right? So this way we'll get an assertion if we ever hit that limit, which I think we want, because we kind of need to make sure that that doesn't happen. Now there is another thing we could do here, and maybe we possibly should. Now that I think about it, it's probably the right thing to do. We know that the leaf count is never going to be particularly high. You know, like a leaf count of 256 would mean that a single grid square had 10,024 axis line bounding boxes in it, which is absurd. So the other thing we could do is pack 24/8 or 2014. We could basically pack into a single 32-bit value, and that would allow us to scale better. So I might also say here, as a separate pass we could do, I'll put a to-do in here that's basically says, look, pack this as a 32-bit value that's a, 24-bit offset with a, 8-bit count. This would scale to much larger scenes more easily. Because it's entirely possible that through the entire grid, maybe someday someone wants to run this engine with more than 65536 possible occluders in it. The chances that they're all on one square are very low. So it seems like what we should do is pack this value to assume that the offset needs a lot more range than the count, right? It's just kind of a basic like bit packing. If you're going to pack a 1616, that implies the two values that you're packing need to be same fidelity, but in this case, we don't really need to do it that way. So we should probably allocate more bits to the thing that we need more of and less bits to the thing we need less of. So taking a look at the grid here, once we've got that produced, I think we're okay. This is the wrong value. I don't know why we did it that way. Let's do that. Okay. So once we do our push array, it looks like the count probably comes first. If it was me, that's the way I would have done it. Yep. And so now we just need to actually do the part that packs these things together. So when we do get voxel index for P, here we already did that right, like so. And so now what we should be mostly doing here is just figuring out how the actual packing packs down into each node. This is the V3S. Yeah, okay. So when we go in to pack these, now what we sort of need to do is we need to figure out, again, like how we want these things to be recorded. And the problem that we're going to have is we don't have like a temporary value anywhere sitting around that would let us do this conveniently. So if we take a look at what we need, something like the one past last index here, where we actually write this down, we may actually want to not quite do that yet. So what we may want to do is something like this, where we say, okay, one past last index just gets initialized to 0. It's going to be used here as a way of figuring out where to fill in these values. And then at the end, we'll just sweep through and divide it by 4, right? Or put it, more specifically, put it into a different category, right? Like put it in, let's see here. So, right, like here, when we're done with everything, we sweep through those grid squares one more time and reset this value to be, what it should be. And again, for that one, so we sort of need to do a little bit of work here. We can't quite just divide it by 4, right? We need these values to be divided by 4 in a way that actually works for us logically. So we need to take the start index and divide that by 4, but then we need the one past last index to be what it would be if we added it, because we know it's a count. We added 3, then divided it by 4, right? because we know that we need to take the start index and divide by 4. You know, you can also think of this as a shift down by 2, right? Because basically what we're doing is we're just taking the high part of it. We know that this thing was already aligned. And again, you know, I'm just going to make it be a divide by 4 here because I think it's a little easy to read, and the compiler will automatically turn it into a shift, I'm almost certain. So we shouldn't have to worry. So what we're doing here is we're just saying, all right, there's a start index. We take one past last index as a count. We add it up. We round up because we need to make sure we grab out that last packet of leaves, and then we divide by 4. That resets everything that we needed to reset. So I think all of this is now correct. This will just flow properly. And so we're really just talking about the packing that has to happen here. And in order to do that, I think all we need to do is use the leaf index, which is given to us directly. So we should be able to basically say, okay, the leaf index is just whatever the start index was plus the one past last index, and that's going to get incremented because we're adding one new one in here. And so I think that's it, right? That just does it. And really, we could just make these you know, I don't really know exactly how we had intended these to kind of come out. If we take a look at the lighting, this spatial grid leaf bit here, right? Actually, it occurs to me too that this total leaf count is just, you know, whatever the value is divided by 4, right? So yeah, I mean, I can't think of anything. Yeah, I can't think of anything squinkier here. But so if we divide the leaf count by 4, we know that each one of these packs 4 in there. We're gonna pull one of these out, and in order to pull one of these out, we need to first, like, I don't know why these are the way that they are. Doesn't look right at all. Like, this just looks, I don't even know how we quite wrote this code. I'm not sure exactly what we were thinking when we pushed this in. It just looks a little busted. So first of all, we don't need this anymore, obviously. But what we need to do here is we need to say, okay, we have a particular node. We now need to take and figure out for the solution spatial grid leaves, which are packed by 4s. We need to figure out what the primary index is. But that primary index is really, that's going to give us back which one of these leaves we're in. And so this part here, where we're doing the leaf index divided by 4, that's really what's going on there, and that's coming from this anyway. So we really can just do this, right? And that's what gives us the leaf in this case. For the lane index is just the mod 4 of the. Well, actually, you know what? I take it back. That's not true. I jumped the gun a little bit there. We do actually still need the leaf index because we can move to a different leaf, right? So the leaf index, we have to do the node start index plus the node one pass last index. That gives us where we're at right now as a count. And then we can produce these two. But that's what we actually needed. So then if we take the primary index here and we go to the leaf, spatial grid leaves, we then have the correct leaf to look up into, but we don't actually know which one of these we're doing, right? So what we want to do there is, again, just use the secondary index for that. So the lane index is what we actually need. This stuff is not really necessary, right? That already happened when we pulled out the leaf. So this was kind of unnecessary. But this lane index part, that part we actually need. So if we just turn these into accessors off of the leaf, we should be fine. And then in terms of these are things we actually have to compute. So what we really want to do is we do want those temp variables, but they're going to be specifically for doing this computation. Okay. So that's what we actually need to do. So when we load up the box, which is what's happening there, right? So it's this box right here. That's where we're actually going to pull those values from. So the ref C in this case is just going to be whatever the ref C is of the box. And similarly, like the emission value here is going to come from whatever the box's pack was. But the box min and the box max are not. So the box min and the box max, what we need to do with those is we need to clip them to this grid square. I'm out of lemonade. Well, lemon water. It's lemons and water. So if we have the box min and the box max enter into this routine, what we need here is we need to have some idea of where the bounds are of this grid cell. So effectively in here where we've got this, right? We need some way of producing the clipping volume that clips this box to that volume. And so where we do the like center, the get center P for the grid square, I don't know, get voxel center, yeah, that. So where we have the get voxel center P, and we pass in the index, that's effectively what we want because that will give us the min-max bounds. What I could do here is say, there's a couple different ways we can. So this brings up another interesting question. I guess it doesn't matter now. But if we take a look at what happens here, we could also say like, oh, okay, so this is how we produce the center. Let's just produce the corners that way too. So let's roll this in here. Let's just say, here's a rectangle 3, get voxel cell bounds, something like that. So if you pass in a particular index, then the result that comes off of this, right, has a min and a max value. And where's our rectangle 3? Yeah, min and max value. And so in both cases, you're going to start with the min corner hot. And in both cases, we're going to do the Hadamard product of the voxel cell dim with the index. But in one case, we're just going to add one additional in each direction. So we would basically just say, whatever the V3 index is, add 1, 1, 1 to it, and that gives us one further, right? So I think that's all we really need for the voxel cell bounds. And so then when we come into the lighting routine and we're building the spatial partition, we can just call this function now, and it will give us exactly what we need to clip to. So in here, I can just say, hey, whatever this like grid square is that we just looked up, so this right here, and we don't need to do that offset because that's only for the grid index. So I can literally just do my V3S XYZ, right? So if I just do get voxel cell bounds here, oops, solution, I can get the cell bounds, and then I can clip these. So these are the box bounds, and I can just clip them now. So I think we actually have an intersection for this, probably. Do we? Looks like we don't. Oddly enough. So you can see here, right, we've got the union, but we don't have the intersection, which is kind of weird, right? I guess we just never wrote it. You can see here that we wrote it for the rectangle 2i, but we didn't write it for the rectangle 3, and it's the same. But this is why you want metaprogramming, just in case anyone was wondering, because it's just does all this for you without all the garbage of templates and stupid stuff that you don't actually want that cause problems in C++. So if you're John Blow and you made your own language, then you're very happy. If you're not and you have to use the C++ committee's garbage, you're unhappy. But, you know, what are you going to do? So the intersection and the union of boxes is just two different ways of using the comparison. In the union case, you take the lesser of the two things for the minimum and the greater of the two things for the maximum, so you expand the size to take the furthest in each direction. And intersecting two rectangles is just the opposite operation. You compare the two, and then you take whichever one was the least in that, you know, along that axis. So you take the maximum value for the minimum and the minimum value for the maximum instead of the other way around. So here, for example, if A is less, then we actually take B, right? Whereas in this case, if A is less, we take A. And then the inverse is true for the maximum values, right? So, you know, not rocket science, but that's the idea. So here we can just use intersect. And so we can say like leaf box equals intersect. And then we can just say, you know, leaf box, you know, leaf box. And this way we have clipped each of our insertions into our spatial partition to that spatial partition. So we know that we wouldn't be producing any intersections outside of the spatial partition ever. So we're never actually going to be in a situation where we collide against something within one node of the spatial partition and produce an intersection outside of that node. And again, that's really powerful because it means we can early out. So it's one of the things that we can afford to do with the grid really easily because we know that the grid is partitioned such that we are pre-sweeping through it anyway. So it's pretty free for us to just, you know, clip those things to the sides of the grid and go from there. I'm going to go ahead and make a box bounds here, I guess. And I'm going to get rid of this because we don't actually care it. And I'm going to say clip the cell bounds and the box bounds together to produce that. And when we actually pull the box out here, I'm going to grab it. Now, I don't know what the Scratch A box index crap was. That was probably old news there because we don't need that to be happening anymore. Scratch isn't used. All of that stuff will go away when we, because we don't need it anymore for the grid. So when we come through here and we do our push array, all of this looks fine. And so the box bounds here is just making a rectangle out of this thing, right? So box min and box max. We should probably have just put a rectangle 3 in there to begin with. We didn't, but something else that we can fix later. Oops. It's just a rect min max, and you know, nothing fancy. All right, so this is the rectangle 3 that we're actually going to use, which is the one that's been clipped so that it's basically the intersection of those two, the actual thing we're testing against and the spatial partition node that we're inserting it into. Looks like all of that code's flowing properly right now through the compiler. Emission is not on there, and so I don't actually know what we did for that. Looks like it's is emission. Is the only difference there? Yeah. So that seems fine. This needs to take the temp arena. And it looks like this doesn't have the temp arena. So what we probably want to do there is to actually get that temp arena. Now, think about this for a second. So I think we actually also don't need to allocate the other, like we don't need to allocate those nodes here. So there's a bunch of things that I can do now, which I probably just should. Because one of the things that you have to remember is like all of this stuff. So like these scratch arrays, like all this stuff, this can all go away now. And like all these box tables, everything. So we'll just be left with these two. And really those things don't persist anyway. Those are things that are only necessary across one frame. So what we can do there is we can actually, even debug lines, like all this stuff is really not necessary to keep in here. So with that per frame arena, the other thing that we can do is sort of change up a little bit about how the lighting stuff is actually working. And we can really streamline this down. So I know it seems really ugly right now, but it's important to remember that you really don't want to spend a lot of time cleaning up code for no real benefit. So when you're actually prototyping and trying to do speed testing on things, you do need to make sure that the code's clean enough that you don't have problems with it that are causing your measurements to be wrong because the code's so messy that there's all these errors in it. So you do need to keep a little bit of a watch on that, but it's really important to not spend time making code clean and streamlined when you're not actually sure if you're going to use it, right? So it's always a little of a balancing act. And on Handmade Hero, like we typically keep the code pretty messy. And that's intentional because until you're actually sure how everything works, any time you spend cleaning it up is usually wasted because what you're doing is you're making the code harder to work with by specializing it towards a particular end. And that specialization then has to get undone later, right? So the lighting system is definitely coming to the point where we could start to streamline it, but until we cross that final hurdle, you really don't want to be making those decisions. So let's go ahead and properly pass the temp arena through here. So in addition to the lighting queue here, I'm going to pass the temp arena for the internal lighting core. And then anyone who is calling that, I'm going to make sure calls. Let's see, spatial partition for lighting. It also has to have the voxel dim with apron. Now, the voxel dim with apron, I guess the thing that I'm a little confused about is the voxel dimension is just something that is kind of there. And I guess the reason that we don't really know what that is because the atlases themselves have those voxel dims kind of baked in. And I guess we don't really know, like when we move those around, like we haven't really thought about, like what goes on there. So I guess to do this properly, what we want to do is say, look, the voxel dim with apron, in this case, is going to come from the spec atlas's voxel dimension, and all we're really doing there is adding two. We're adding, one extra pad on all the sides. So I think that's really it that we would need to do there. And I think that's it. So the end temporary memory, I don't remember exactly how we did this in Handmade Hero specifically. Okay, so it's just a temp mem. So basically we have a temp mem that gets set by whenever we began the temporary sweep, and then it gets reset at the end. So it just looks like that. I think that's about it. In the test raycast for here, I guess I'm not sure what we are still doing with this particular routine. So I guess this is just the stub that we use for testing, so that makes sense. I thought we called internal now. Does anyone call test raycast? Nobody does. So this is not a thing. So that just kind of goes away, right? So here where we call internal lighting core, we need to pass a temp arena here. So we need some way of giving this thing something. And if we take a look at what a memory arena has in it, there's some issues. So the platform memory block bit of things here is a little bit of an issue, again, because we don't have that structure in the test code. But the nice part is we can just make it so that the platform memory block that we give it is so huge it will never have to allocate anything. And then we don't really have that problem. So I think what we can do here is say that there's a temp arena, and then the temp arena dot current block can just be something that we actually pass that's some large allocation. So platform memory block, like this. We can just stuff this with values that are sufficient for our needs. I think that should work. And so in here where we do these allocations, and I believe in here we do malloc these, right? Yeah. So when we do a profile run with a repeat count thing, when we do these mallocs here, and we set up like the arenas to work with this stuff, we don't really care about how much memory we throw away here. It's not super relevant to us. We just need to make sure that our temp block has enough space. So the flags on the temp block don't really matter because no one's going to look at them. But the size, the base, and the used all do. It's really just the size and the base because the used being 0 is what we would want. So the size of this is just however much we think we need. So, 16 megabytes or something. I mean, how much is this really going to use? It's not actually using a particularly large amount of memory. So I can make the base address just be something that malloc gives us that has that much room. And then that should be sufficient for the memory arena to function. That's my assumption anyway. So if we pass the temp arena into the internal lighting core, I don't quite remember the order of passing here. So the debug repeat count comes last. So that should do it. And I think that's all we need. So I think that's everything for building the spatial partition. And it should just work as long as we do a step through it and debug any of the obvious bugs. Like it shouldn't be particularly hard because, again, it's just gridding up those boxes. And I suspect that the only real problems that we may run into are like indexing because, like I said, because it has that apron problem. Oh, and that's something we also will need to do is I should probably just do that now while I'm thinking of it. We will need some way of making it so that there's the apron around it is set specially. So when we go through here and we look at these nodes, we need to set certain ones to be marked as apron. So I guess what I would say is, like, in here, what I'd do is, we set this up as we normally would, and then we'd have an if, and the if would be based on the grid Raycaster, how it's doing that check. So you can see here, it looks to see whether the node start index is a spatial grid terminator, and if it is, then it doesn't proceed. So what we need to do here is we need to do a check and say, well, is this particular grid index on the edge or isn't it, right? And I'm not sure what the best way to do that is. It might actually just be... it might actually just be to clear to that. Right, you could just do this. And then the start indexes of all of those are all spatial grid terminators all around. Then these, as we go through here, these get sort of set up properly as long as they weren't set to that, or as long as they have a, yeah, because this wouldn't know the difference between those two, though. So that doesn't really help. Yeah, so no, I guess that doesn't help. So I guess you kind of just need to actually do one loop that is actually proper along the voxel to set this. I don't know how else you would do it. Yeah, I'm not sure. So I guess you just need to do something like this. Maybe I'll just do it in line. I don't know. That's a tough one. So if I were to do a full sweep of the voxel, so, you know, something like this. And here we go and say, well, all right, we're going to go through each of these. In order. So each of those things, and we, oops, I don't know why that happened. And we can now just test against those, I guess. Oops, that was, all right. So in here we could say, if we loop over the voxel and we grab out the grid index from voxel dim with apron, XYZ. It's not a particularly efficient loop, but after we grab out the node, we can do an if and check to see which one of these two we want to do. And we can just say spatial grid node terminator. And furthermore, I suppose we can decouple these. You know, it can do that assignment, and then it can just do a conditional assignment here because we don't actually care about we don't care what this value ends up being in that case. And so what I might do is just say, okay, take the start index, assign it to the one past last index, assign it, and then possibly overwrite this if we happen to be like if z equals 0, you know, or y equals 0, or x equals 0, or z equals voxel dim with apron z minus 1, or and that will properly terminate the apron so that we know we're not going to have any raycasting that goes outside of that. And hey, that was convenient. The stream ended right as I finished that routine. So I feel like that will properly spatially grid up our stuff, modulo cleaning up for bugs. And so that leaves us with one more thing to do tomorrow before we can start actually cleaning this up and going, like doing speed testing and debugging and all those good things, which is to build those tables, because we don't have those tables built. Now we did sketch out the thing that builds the table, so you know we did do that, and like I said, I don't really remember where we actually put it, but we did build that, and so we should be able to then take that code and make it actually work, and then we can have all of our tables that we need. There's one thing we'll have to add to it, because my recollection is that we weren't keeping, well, no, maybe we were. So we may actually have already been keeping T throughout the whole thing too. Now that I think about that, that may actually be, yeah, it is. So here's compute walk table, and yeah, it looks like it accepts a new T each time. Is that correct? So it's like setting up the location. So it takes the dimension step and it sets that up. And then each time through, it starts T best at F32 max. And then it looks through each one to see which one it will go to first. So we more or less are tracking the T through. Because we know the at value. So, I mean, I think all we would really have to do is just take the dot product along the ray of the at value, and then you're pretty much done. So, like, I think that just solves the problem, right? So for example, here, if we, every time we do a termination, so we come through here and we want to know where the T terminate was for a particular walk. So I guess it would actually be here, right? So if you want to know what the T terminate is for any particular walk, you would just take whatever the at value is, I believe, of this one and not the previous one. I guess. I think it's this one. So the T terminate value is just whatever the at value is. It would just be the inner product, right, of the ray direction and that at value minus whatever the starting location is, because that's just going to measure how far along the ray you've went. So the T terminate value is just known. So we can now put it directly when we build the table, so it's pretty easy. The question is, do we really want to store it? But it's easy enough to store. So we could build this table pretty trivially. This looks like the correct actual call. Seems fine. And yeah, I mean, so I guess like we've pretty much already done the work. So tomorrow it's just going to be a case of like actually cleaning it up. All right. So let's see what happens. Let's go ahead and go to the Q&A. Someone said I might have had a typo on that last one. Let me clean that up while people are... Yeah, you're right. This should be an X. I agree that that was a very good question that Insobot created. I already talked about the UE5 demo during the pre-stream, but I did not actually watch the demo yet. Can you watch the demo live? I can if I stop the recording. YouTube is really bad about copyright claims. Like you can't, like when I go to upload this, like they will like copyright claim your whole video because someone, you watch a 5-minute clip of someone else with music in like a 3-hour video that like literally no one would ever think isn't fair use, but it's an issue. So I could stop the recording now and we could go watch the demo, which is fine. I don't see any questions. So if people want to, if they do have questions, they could save them tomorrow. I could go watch it, but let me stop the recording because I don't really want to have that be. What was the original justification for switching to probe-based GI? So the reason for that was that I couldn't really figure out. So let me say two things about it. So the first thing is that we had no solution. Like we needed to solve for the lighting in general. We needed to have a solution that would light sprites, right? Because we have lots of sprites and they need to get lit as well. And we hadn't really quite figured out how we were going to do that. And the reason that I hadn't used light probes in the first place, because we basically did do a light probe system even originally, it just was point-based light samples around the geometry. The reason that I hadn't done a light probe in the first place is for some reason I had like this mental block of not figuring out how I could do the initial propagation with the light probes, because I was like, well, how do you figure out what they're actually lit by? And I was like, for some reason, never put it together in my head that when you do your light propagation, you just sample the light probes for your light propagation. It's kind of fairly obvious, right? I don't know. It was just, sometimes you have mental blocks on things. Programming is very complicated. And graphics, 3D graphics is very complicated. And sometimes you just like aren't thinking clearly about something. So even though the thing is not particularly difficult, it's just because there's so much complexity involved all around the thing, you just miss this, what would otherwise be fairly straightforward. So I think like my feeling on light probes is they're probably what we should have done from the beginning, but we didn't do them because I didn't quite know how to solve a particular problem with them that really isn't a problem. And so once we figured that out, it was fine, right? So that's all really I would say about that. And the nice part about light probes is now we can light our sprites with them because we can just, in the pixel shader, we already do, in the pixel shader, we can just look up what the light probes are neighboring to our sprite and just light them and off we go. So it's very nice. And it solves all of our problems for us. The grid-based raycasting, I think, is awesome now. I hadn't considered the fact that I can terminate rays anywhere I want and then just fill in a value there with the light probe. I've literally never seen anyone say that. I don't know why. Maybe because it's so obvious that it doesn't need to get said, but it seems like a really, really big strength of grid-based, of not just grid-based raycasting, because I've done grid-based raycasters before. In fact, Granny has a grid-based raycaster in it. It's how it does normal map transfers from high-res to low-res models with a grid-based Raytracer. So I'm actually very well versed in grid-based Raytracers. I just never wrote one for actual lighting that was using a light probe system that happened to be aligned to the spatial grid. If you actually have light probes aligned to the same grid that you're using for culling, it becomes really pretty, and I guess it doesn't even really have to be aligned now I think about it, but just in some way that you can get a light probe answer anywhere in space, it's pretty compelling because you can always choose to terminate early. I don't know why I've never seen anyone say that. Probably, again, because it's so obvious you don't need to say it, but you probably should say it because, I don't know, I didn't think of it right off the bat for whatever reason. Maddie Manzani has a question. Did I remember correctly that our lighting partitions aren't fixed in world size, but are fixed in number among XYZ? Does that mean we can't have the ideal situation where the lighting voxel is aligned with world blocks and light voxel size is a multiplier subdivider of the game grid size so that most of the lighting occluder voxels are not partially filled, but mostly filled? So actually, it's a little bit different than that. We haven't specified a rigid policy on this yet, but we do have something in place for it right now, just for correctness. The real reason that we're doing what we're doing is because when you subsample lighting like we do, you have an issue that anything you might do that changes the basis of that subsampled version could be seen as an animating artifact. So for example, let's suppose that we, between every other frame, switched between twice as dense a voxel grid and half as dense a voxel grid, right, oscillating. You would see that animated error very clearly as the lighting just changed every other frame, and it would be like kind of flashy and weird because it's subsampled, so it's not a correct solution everywhere. It's an approximate solution, and when you change the ground underneath that approximated solution like that, it will produce objectionable artifacts over time. Any given still frame will still look just fine, but when you'll see that change. So what actually happens in the system currently to prevent anything like that from occurring, even though we move the lighting bounds around a lot to like fit them over the space you're seeing, all we require is that you always align yourself to a grid that is the voxel size grid, right? So it doesn't really matter how they line up with world chunks in any particular way. They just have to always line up with those chunks in a consistent way. So as we slide the lighting volume around, it just always has to line up properly with the same basic like grid in world space. so that if we move it, it moves exactly one whole voxel square over, so that the lighting is always the same and doesn't slide, right? So that's all we're doing, is we're keeping ourselves aligned to the voxel grid no matter how we move around space. That's the only thing we're doing there. And we have to do that or you would see an animation error. Could you put moon blocks in the apron so you always hit something instead of using a special index? Unfortunately not. And the reason for that is because the problem that we have, and it's not a problem. It's more just like something we need to decide how we want it to look and how we want the processing to work. It's not like a problem in the like bug sense or how are we going to fix this? It's pretty straightforward. But the problem that we have in this case is that we don't actually want moonlight to light anything underground. So when you go down the stairs, we don't want moonlight lighting those rooms unless the moonlight could have gotten in through like the ceiling, like the stairwell, right? And so the problem is not that we couldn't put moonlight or like ambient light tiles in certain places in order to make that be the termination condition. The problem is most of the time that's not actually what we want, right? I guess I'm not sure how else to say that. So basically the problem that we're trying to solve here is more that we need to control where the moonlight actually is, because we don't want you to be able to hit moonlight from underground things. And I don't think we want to have to put ceilings on them, right? So what I'd rather do is just put moonlight emitters maybe on the outdoor rooms so that they hit those emitters and are processed that way. I think that's probably the way I'd rather do it, but can you move the play button on the page a bit down, because on first glance the horizontal line of L lets it look like it has a partial drop shadow? No, I can't. Maria Manzani says, oh, so essentially every lighting voxel dim is consistent across frames. Yes. The lighting voxel dim is consistent across frames, even if the camera zooms in or out. That's correct. I thought that voxel dim was calculated by taking world region to render size divided by max number of lengths. No, I don't think it is. I mean, I could be wrong about that, because again, I only work on this on weekends, and I have a lot of other code that I need to worry about. But I'm pretty sure that's not the case. What's my best shot at getting a standalone C++ compiler bundled with my engine? Probably Clang would be my guess. C compiler, one of the nice things about C is it's a very straightforward language and the compiler can be written fairly cleanly. C++ is a giant disaster. If you actually require C++, the full language, I mean, it's absolutely horrible. And I mean, the problem is with C++, 99% of the language features in C++ are not good. So you basically pay a tremendously huge cost and have a very complex compiler and you get nothing for it, right? So I guess what I would say is like, yeah, it's C++ is terrible for very, very many reasons. And among all of those reasons, a very large one is it's prohibitively expensive to build your own compiler for it in a reasonable amount of time, right? Like it's one of those things where, you know, like if you told me that I need to write a C compiler by next weekend, I'm like, okay, I can probably do that. If you tell me that I have to write a C++ compiler by next weekend, I'd just say it's not possible. Like we have to use someone else's code because there's no way we're going to make that work. You know, the spec alone, just even reading it to understand all the things that you don't probably know about C++ that you need to handle is prohibitive. I mean, it's impossible. So I would say, like, you know, first of all, are you really sure you want to do that? And then second of all, if you are sure that you want to do that for some reason, I would strongly recommend using someone else's code. On Handmade Hero, we don't use other people's code because the point of the show is to show how to code things from scratch. That's the whole point. But that doesn't mean that that is the right choice in all circumstances. And if ever there was a circumstance where it's probably not the right choice to roll your own, it's C++ compiler, because what a waste of your time. Holy cow. Do you think const is useful for function arguments? No. I don't think const is useful, period. I think for other programmers, sometimes it's useful. For programmers who make mistakes about what they can and can't write to, I pretty much never make those mistakes, as you can see. I think we've talked about this many times. So if you look at the kinds of bugs that I have often, they're often indexing bugs. And indexing bugs aren't caught by const, right? If you're the kind of programmer who oftentimes finds yourself writing to the destination and not the source, or the source and not the destination, if you spend a lot of time finding bugs like that, that's where const can help you, right? So, but I think through the entire Handmade Hero, which is the worst case because it's like I have the least mental resource I'm trying to explain the whole time, I think we've had one case of writing to a thing where const would have caught it. It's like pretty early on. So it's just like, what a waste of time it would have been, right? To catch one bug that didn't even take us hardly any time to find, right? We would have spent all that time typing const all over the place for literally no reason, right? What do we call it? Like, on Handmade Hero, it's just CL. It's just CL. But CL is like Microsoft property. You can't distribute it with your game, right? Clang has some kind of a GPL license or something. I don't know exactly what the license is for Clang. I mean, go look at what the license is, but the point is, Clang is licensed in a way that allows you to include it in commercial products, right? And CL isn't. So the reason I said Clang when you asked what would I do if I wanted to be able to include a C compiler when I ship the game is like Clang has a license that you could comply with, but in CL is not. So, you know, and there's nothing particularly wrong with Clang. Clang's a good compiler. It sometimes produces better code than Microsoft. Sometimes Microsoft produces better code than Clang. But so, you know, there's no real reason to use one or the other. You can use either. So if one of the things that you're targeting to try and do is to ship the compiler with your game, then, you know, Clang's the obvious choice. It's, you know, it's totally reasonable compiler. It's, you know, 50-50 as to whether you'd rather have it or Microsoft's, and so it's no difference, just use Clang. All right. So I will go ahead and do as I said. After I close this down, I will watch the Unreal thing. So I'm going to do the stop recording here.